All right. All right. My name is Fred, and greetings to everybody who have got access to this video. As we previously agreed that we will have a session on question 3 and 4. They're the same way, the way that we're having it right now. So maybe in the next 15 to 20 minutes, let's just look at it. Let me share the question. So I'm sure you've looked at it previously when we, after our session last week. So I hope that you have. All right, so it says that a process consists of an integrating element operating in parallel with the first order element. And then you've got a diagram there that is a representative of what that says. So you've got your inputs, your outputs, and those there, K1 and K2. So the first question was asking you to find the overall order, or yes, the order of the overall transfer function, right? So what you needed to do was to come up with an expression for GRS, given the information that you're given, and write it in standard form, the form that you're supposed to write the transfer function at, and then from there you can pick the order from that. So let me quickly give you the form that we're expecting at the end of this. So we're expecting you to have your GRS in this form, GRS. This is not the final answer to this particular question, but the form that you're supposed to have your transfer function at to be able to pick up the overall order. So you can have K, so it's GRS is equals to K, tau A, S plus 1, all divided by tau 1, S, and also plus 1. So the reason you've got tau A there is because it can be consisting of both K1 and K2. That's why it's not tau 1 or tau 2, but just tau A, because it can be consisting of different variables there on the inside. But as long as you've got that tau A there and the S plus 1 and the K on the outside, all divided by tau 1 S plus 1, and then that will be the form that we are looking for. So from that, just this form that we have here, you can see that, oh, the overall order is 1, because on the denominator, the highest power of S that we can have is just 1. But if we add another S here, these and these will multiply and the overall order will be 2. So that is something to look for. So now let's go and quickly derive our expression for G at S. So for us to get our expression for G at S, we first need to relate our inputs to our output in this particular process that you are given. So how do we do that? So for us to get the G at S, we first need to find the expression for our output, which is Y at S, and then we'll just simplify from that to get our transfer function. So what we will do is we find the expression for Y at S, which is just this, multiplied by your input, plus this, multiplied by the input again. So you're just gonna have K1 over S multiplied by U at S plus K2 tau S plus 1 multiplied by U at S also. So we just simplify from this to get our expression for G at S. Remember, it's also given in the equation that G at S is Y at S over U at S. Pardon me if I'm too fast. I'm just trying to have a shorter session. Which will play a very big role when it comes to the sharing of the video. All right, but this is also up for discussion after we have shared and everybody have got access. All right, so what you could do there, as you can see, you can factor out U at S, because at the end you want to have an expression for U, Y at S multiplied by, divide by U at S, right, which is equal to G at S. All right, so you can factor out the U at S. You can be remaining with K1 then, divided by S, plus K2 divided by tau S plus 1. These will be your Y at S, but remember you want G at S, which is Y at S over U at S. Then you can go and divide with U at S, divide with U at S on both sides. You see that on the right-hand side, they'll cancel, and you'll be left with G at S, because that is the same as G at S, or is equal to G at S. We'll have G at S is equal to K1 over S plus K2 over tau S plus 1. But now remember, you cannot go and pick your overall or the order from this expression as it is. You need to have the expression in the right form of a transfer function. And the form that you're looking for, I wrote it before we started this calculation. I just hope you wrote it down while I was also writing it. All right. So now let's simplify that. Or maybe did you not see that? Let me just undo that and have you see that once more before I clear it. Should have given you a warning there. All right. So that's the transfer function that we ended up with. K1 over S plus K2 over tau S plus 1. But that is not in the right form, right? You need to manipulate it to have it in the right form. All right, let's clear everything. So how do you then manipulate it? What you do is you get your LCM or LCD, whichever. So what you're gonna do is you're gonna multiply both the denominators of each terms, and then you're gonna have S tau S plus 1. This is just mathematics. So you're just gonna have K1 there on top, tau S plus K1 plus K2S. So that was just mathematical manipulation. I don't think it's really necessary to be showing that in detail, but I think you are very much capable of doing it yourself and try to get here, right? So while you're having it like that now, you can factor out the K1, because in each term, in each of those, you can see that you've got K1 in the first one and K1 in the second one, but the third one doesn't have K1, so you just leave it as it is. So what you're going to do is you are going to say, okay, I see. We do not factor out the K1, rather we factor out the S, right? We factor out the S because that's what we want outside, or that's what you want to be multiplying with our tau A. All right, so I'm sure you've picked that up by now. So what we are going to do then is we're gonna take S on the outside between the first term and the third term. Those are the only terms that contains S. And then you're gonna have K1, then plus, it's gonna be K1 tau, right? Or let's just write tau K1 plus K2, because we do not have S with K1, with the other K1, the one in between, we're just gonna say plus K1. All right, and then your denominator, you're still gonna have S tau S plus 1. All right, I hope you see what is happening then there. So when you have it like that, I'm sure it looks like you've done much, or it looks like you've done all that you can. But remember, in our general form, right? The form that will have K divided by a function of S and tau in the denominator. So you need to have a function or a transfer function that have got K multiplying with something. So in this case, you're talking about K1 multiplying with the rest of the things on the numerator, which in this case now you do not have. So what you need to do then is for you to factor out the K1. And when you factor out K1, this is what you should remain with. You should remain with K1 multiplied by tau plus K2 over K1 multiplied by S plus 1 and all divided by the same thing. There's no change on the denominator. Tau S plus 1. So this is the form that you want to get to, and from here you can easily pick up your order, right? So what is the order? So if you can look at your denominator, the maximum exponent that you can have there is 2. That would come from this S on the outside multiplying with the S that you have there. So the maximum exponent you can have on the denominator is 2 from those two S's there. So it simply means that your overall order is 2. That is the order of your G at S, the order of your transfer function. So let's look at B, right? We're done with 1. Let me clear everything. So B now, it says what is the gain of G at S, right? The gain is just K1, like you saw when we factored it out there. The gain, because we don't have any values, gain is K1. The order was 2, and the gain is K1. All right. All right, it's fine. And then now we go to C. What are the poles of G at S? Where are they located? In a complex S plane. So this, if you have been consulting your notes, it should be very easy for you to go forward with. So the poles of G at S are because we have written our transfer function, right? So you know that the poles will look at the denominator and the zeros will look at the numerator. Don't forget that. So your poles, if you can solve for that, we have been solving for that in previous questions. Your poles, the first one is going to be 0 and another one is going to be -1 over tau. And where do they exist? If you want to check where they exist, I don't think it should be something that you can try to find by plotting, because you only have got the poles only. But where you'll find them, let's just address this. Where you'll find them, S1 will be on the imaginary axis and S2 will be on the left-hand plane. But when we say the imaginary axis, remember the imaginary axis, we were talking about the axis that have got the J values, right? And the last time we met, and even on previous questions, we looked at it in terms of that it will be, the imaginary axis will be on the y-axis. All right, so D, you've got D that asks you for the zeros now. The zero of G at S. Remember that let me just rewrite our transfer function so that you have got a clear reference if you haven't been writing it down. So our G at S that we found was K1 multiplied by tau plus K2 over K1 multiplied by S plus 1 all over S tau S plus 1. Remember, this is the same arrangement as our general formula that we wrote there for the transfer function. So if you can look at the general formula, this represents tau A, right? It's just the same thing that we were talking about. All right, so there's no difference there. So this is the transfer function that we got, and now we need to answer the question that says what are the zeros now. So if you can look at our numerator, right? You are looking for the zero that will be in terms of SA, right? Because your tau A is existing there. So how are you going to do this now? You're going to solve for S on your numerator, but that S, you're going to call it SA because it's S that was calculated from the existence also of tau A there. All right, so if you can try to do that, you just need to go and say this whole part. Let me change color for clear reference. This whole part is equal to 0, right? And then solve for S. So what you will do is you'll go there and say tau plus K2 over K1 multiplied by S plus 1 is equals to 0. You take the minus 1 on the other side and then continue to solve for S. And then the SA that you get, remember we said S is SA, right, in this term. So you're going to get minus 1 over tau plus K2 over K1. The rest of the things are just to enhance your focus. That's why you find me not writing everything that I say, because I want you to be able to write it whatever you're writing and be able to follow through your own steps. But this is enough. All right, so that is what you get, right? But still, when you write your zeros, right, you have managed to find your zeros, but there's also a question of where are they located? Is it the right or left hand side, or maybe right or left half? So okay, this is asking about halves. It's not just about the side. So it's right or left half of the S-plane, right? So you need to understand. And they also ask under what conditions or condition will one or more of the zeros be located in the right half S-plane. All right, so it's quite interesting. So for you to establish that, you need to write your SA in a form where you will have your gain on top, right? So it simply means that you need to simplify this in a manner that you will have K1 existing on the top and K1 alone. So how are you going to do that? You're going to solve and manipulate. So when you do that mathematical manipulation, you're supposed to end up with SA is equals to minus K1 over K1 tau plus K2. So how you establish that is also up for discussion, but I like maybe for you to try it out. Maybe if it pops up in your test, you might also know how to go about that because you've tried it at some point. So I want you to also try it out, how to convert that to that. So when you have it in that form, so now you ask yourself, they say under what conditions will one or more of the zeros be located in the right halves of the S-plane? So if you can look at that, it's a negative answer, right? It's minus K1 something something, right? But we were looking for what? K1 over there, that. So this is negative. So what we are trying to say at the end of the day is, let me erase this so that we can have a bit of space. Now we're left with about 10 minutes to wrap this up. So hopefully everything works in time. So what you need to do there is, because you can see that your K1 over K1 tau plus K2 is less than 0. It's less than 0 because you can see that there's a negative sign existing before that. So when it's 0, it's in the right, when it's less than 0, the location, right? This being less than 0 will also tell you something about the location. So it's in the right half plane. So how we establish that, it forms part of your slides. I think in part 2, you can also see different conditions and also various examples there. All right. So in the next 10 minutes, let's also try to wrap up. So when it's like that now, how would you get that conditions to be well established, right? That can only work if the conditions will be your K1 is less than 0, right? When your K1 is less than 0, it with that negative sign, there will become a positive, right? And the second condition that goes with that one is your K1 tau plus K2 is greater than 0. That this is a positive answer. So if that is a positive answer, then it's positive divided by positive to give you a positive answer. So with that, you would get your 0 in the right half plane. But you can also look it up and try to do other slides examples. All right, so now let's also look at F. All right, so with F, it says that for any input change, what functions of time response mode will be included in the responses Y at T, right? So this forms mostly part of your theory, and it's not something that is worth going over on this platform for the next 2 minutes, right? You're gonna have a constant term and e to the power minus t over tau term. All right, also worth discussing on another platform. We can also have that discussion on WhatsApp, or you can reach out if you're not getting it on your slides, but it's there. All right, so let's also go to G. If so G says that is the output bounded for any bounded input change. For example, U at T is equal to M. So this is just the analysis, and everything is just based on the things that you're given on your slides, right? So there's nothing new on this on this one. So try looking up the answers and maybe how to do the analysis from your slides, but the answer that you come up with, that it should be that if input is M over S, right, the output will have to contain a T term that is not bounded. I hope you got that. So if your input is M over S, right, the output will contain a T term that is not bounded. But I think you can also look, is there. All right, it's there. I'm just saying that we are now left with about 8 minutes to wrap up. So let me not consume that time. All right, so let's go to the other question, which is question 4. Question 4, consider a transfer function below. G at S is equal to 321 minus 4S multiplied by e to the power minus 3S divided by 24S squared plus 28S plus 4. All right, so the first question was, what is the gain, time delay, time constants, poles and zeros of this transfer function? All right, so for you to have that, also still, you need to write it in the right form, right? So the only thing that you need to do on this particular one is just to you need to factorize, right? It's something similar to what we have done on the other questions during our meeting. So for you to do that, you can see that on both the numerator and the denominator, you've got 4. So if you can factor out 4 here from the denominator and 4 there, the numerator, the 4s will divide, and then you will have it simpler. Simply means that on your numerator, you're going to have 18, 1 minus 4s multiplied by e, 3s over. You can also factor out the answer that you get there, because this is going to be divided by 4, this divided by 4, and that is just going to be remaining as 1 now. So you can also factor it as plus 1. This will help you with the determining your poles. So it's already in a simpler form. All right. So what is your gain? Your gain is 80. All right. Remember, we talked about writing it in simpler form, or the transfer function in the simplest form, with one of the questions when we met during our session. So we're just executing the same thing. So the gain, our K, if you can even have the expression of the general formula, our gain is 80, and your time delay, you just have to pick that up, is 3, and your time constant, tau 1, right? You just need to pick that up also, and you'll find it to be 6, right? And your tau 2, you just need to pick that up also. You'll find it to be 1. And your poles and the zeros, that one self-explanatory. We have been solving that ever since. So your zeros, just the roots of your numerator, and your poles, just the roots of your denominator. All right, so you're gonna get your poles as -1, and the other one is gonna be -1 over 6. And for your zeros, you're gonna get 0.25. All right, so this question is just similar to the one that we did in class in terms of question number A, or question A. All right, So will the step response of this transfer function exhibit? Will it be an inverse response or oscillations? And we need to justify that answer. So how will that work? What idea do you have there? Do you have any idea? Just think about it. Think about it. Think about it. Will it be inverse response or oscillations? So this is something that you can also get from the theory that you have, the theory that you were given, right? So will it be oscillations or that? So the condition that is existing here is that your tau A is -4, right? From this transfer function that we have. If you can look at the general formula and look at the location of tau A, you will see that your tau A is -4, right? And when it's like that now, simply means, in fact, do you guys even know why your tau A is -4? Remember, we said that here you wanted to have K outside, right? Which you do, but you also wanted to have tau A multiplied by S here, right? But at that point, maybe you to be a point where you've already also derived or resolved your time delay, right? So when you solve for that, your time, your tau A at that point will need to be -4. But please write it down and have sequential steps to see where that leads you, because you need to be able to understand this. So your tau A is equals to -4, and then which is less than 0. And this condition from the notes that you're given, if that exists, then you're having an inverse response. So also look at inverse response conditions and also oscillation. The conditions for oscillations. I just hope this was informative, and we need to call it a wrap. Apologies if I was too fast, but we had to, so that we can end up with a shorter video that will be of convenience to everyone. All right, if you've got any questions, please feel free to discuss this in the group. I'll also be there to attend to that. And make sure that you're not left behind on anything that we are doing here. It might be of great importance when it comes to your test, understanding this and every aspect of it, and also being capable of mathematical manipulations. All right, in that case, that's it, guys, and see you on the other side. Bye.